So good morning, everyone. Yesterday we tried transmitting this lecture live, but it did not work. Either some problem with my internet connection or with the server. So I recorded it, and I'm going to transmit it on YouTube, so you can access the material. This is part of a lecture, which from the mechanical engineering course, which was supposed to be done in person, but we are in this situation with the coronavirus crisis, so we are doing our lectures remotely. So we are talking about isothermal transformations, and just to remember, we started our semester with a revision of the iron carbon diagram, and the iron carbon diagram is very good, very useful. We can use it to understand the formation of microstructure in steels, which are processed with very slow rates of variation in temperature, which are the equilibrium conditions. But if we want to understand what happens in a steel which is submitted to non-equilibrium transformations, so if it is cooled or heated more rapidly than what is necessary to assume equilibrium conditions, then we need to have some other tools to understand the phase transformations and the resulting microstructure in the steel. We started looking then in the second part of the course to aspects of phase transformations, and we basically divided phase transformations into two groups. We have our diffusive transformations, which are those in which the predominant mechanism is atomic diffusion, and we have our displacive or martensitic transformations, in which the predominant mechanism is distortion or deformation. We are concerned right now with the kinetics of diffusive transformations, which are transformations that, because they depend on diffusion, they happen gradually over time, normally at high temperatures. And they happen gradually over time in two stages, which are nucleation and growth. So we discussed what these stages were. We presented models for nucleation, for homogeneous nucleation, for heterogeneous nucleation, and we developed expression for the rate of nucleation. We also developed an expression for the rate of growth of these nuclei. And so this was already done, but just so we can remember, G dot is the growth rate, which increases with temperature. N dot is the nucleation rate, which has a maximum at a certain value of supercooling. Sorry, this is the overall transformation rate. So the nucleation rate has a maximum value for a certain supercooling below the equilibrium temperature, Tm, and the overall transformation rate, now the blue curve, is given simply by the product of the nucleation rate by the growth rate. Now, for practical reasons, it's difficult to measure the growth rate, or sorry, the rate of a transformation. What we can do, or what's easier to do, is to, instead of the rate, we measure the time, for a certain fraction of the transformation to happen. For example, imagine we are following the transformation of water into ice. So we take water and ice, we leave them at a certain temperature, and then we can measure, for example, the time required for half of the water to transform into ice. If we do that, then we can simply take this graph of temperature by rate, and we can invert the horizontal axis, and we get this curve, this behavior. Temperature time diagram, which is simply the other one flipped. So, and we could do this for any transformation that happens by diffusion or which happens over time, and we don't really have to take the arbitrary fraction of 50% or 0.5 like in the previous example. What we could do is we could take, for example, the time required for the transformation to reach 1% at a given temperature, T1, and we could then wait more and see how much time we need for the transformation to reach 99%. And we could do that for many temperatures. We could do this for T1, for T2, etc. And then we could build a diagram which is composed of two curves. One curve which represents the time required for the transformation to start at a given temperature, and the second curve, this one, which represents the time required for the transformation to end or to reach 99% of its completion at a given temperature. What we want to do now is we want to have a look at how the transformation evolves over time at a given temperature. So we want to see what the kinetics of an isothermal transformation look like. So we're going to do some little theory here. We are assuming the transformation we are talking about is simply alpha transforming to beta. We're assuming it happens by nucleation and growth. So we have nucleation, the appearance of the first particles of beta, they start growing, and then we would form the final structure over there. By considering homogeneous nucleation with a constant nucleation rate m dot and a constant growth rate g dot in a total volume V, then we can state the following. So we are interested here in developing an expression which relates the transformed fraction or the volume fraction of phase beta, which I'm going to call simply V beta, with time. To do that, we need two things. We need the increment in the number of nuclei, which is simply going to be the total volume of the material times the nucleation rate times an increment of time. We want an expression also for the radius of the nucleus as a function of time, which is going to be called r, and this is going to be g dot multiplied by t minus tau. Why do we have this tau here? Why do we have two constants for time? It's this. The t is the overall time of transformation, and tau is the time scale for the nucleus. So, why do we have this? Imagine 10 seconds have elapsed since the beginning of the overall transformation, but a certain nucleus has only appeared after 5 seconds of the transformation. So it will not have grown for all the 10 seconds, it only grew for 5 seconds, 10 minus 5. So that's this. And if we multiply, if we take our increment in the number of nuclei multiplied by the volume of the nucleus, then we have this expression for the increment in phase beta. So here we have simply dn, which is this term here, and the volume of the nucleus is so we just consider the nucleus to be a sphere. And I call this volume, or this increment in volume, V beta prime, because it's not the actual volume of phase beta, and we're going to see why it's not the actual volume of phase beta shortly. Well, we can solve this by integration, noting that all this is constant with respect to time, and then we get an expression for the volume of beta. Now, why is this not the actual volume of beta? This is actually a sort of extended volume, because to develop this expression, we took into account that the volume available for nucleation was always the same throughout the process. And this cannot be true because, for example, once we have nucleation and growth, we cannot form a new nucleus of phase beta where we already have phase beta. So what we need to do is we need to correct the available volume for nucleation as the process keeps moving. This is valid. This here is valid only for very small transformation fractions, so for the beginning of the process. Therefore, the actual volume increment is corrected in this manner. So dV beta is the actual volume increment. We're going to say it's equal to this extended volume increment multiplied by the percentage or the fraction of the volume which is still not transformed. How can we write the volume of which is not transformed yet? We simply say it's 1 minus the transformed fraction. So V beta by B is a transformed fraction. So we can solve this again by integration, and then we get that the extended volume V beta prime is given by the natural logarithm of 1 minus the transformed fraction, or V beta by V. We can combine the two previous equations, and we can call V beta by V, we can say this is just some variable y. Then we can rearrange this to see that the transformed fraction y equals 1 minus the exponential of minus k multiplied by t to the power of n. In this expression, k is this constant here, which is simply the terms of which were here initially. and n is ideally 4, so it's the time exponent 4. This is a very important equation in physical metallurgy because it explains the time variation of transformed fraction at a constant temperature. It is due to these four gentlemen, Johnson, Mel, Frommy, Kolmogorov, and it's called also the JMAK equation. The JMAK equation is shown here in idealized form. It is a sigmoidal curve. So this is the ideal schematic depiction of this JMAK equation. To see how we can use this in relation to some concrete situation, let's consider the following example, which is an example that you have, which is very similar to one example you have in your exercise list. What do we have here? So samples of a cold worked low carbon steel were annealed at 600 degrees for varying times and then cooled down to room temperature. After cooling, Vickers hardness measurements were performed and the results are presented below. We are asked to determine the JMAK equation constants K and N for the recrystallization process in this steel. So what happens is basically we have a steel which is initially strain hardened, which is put in an oven, heated to 600 degrees for various. So different samples are heated for various times, and hardness decreases due to recrystallization, such that the hardness drop can be considered an indication of the transformed or the recrystallized fraction. So the first step we need to take to do this example is we need to convert, or we need to make an estimate of the recrystallized fraction y based on the hardness values that we have. And the idea here is very simple. We will assume that the hardness decrease is proportional to the recrystallized fraction. So we have an overall hardness loss, delta HV, which is 180 minus 115. So we are assuming that the initial hardness corresponds to a zero amount of recrystallization, which is good because it was not even heated. Time was zero for this case, and we are assuming that 115 Vickers hardness corresponds to the complete amount of recrystallization. So it's the end value. So the overall drop in hardness is 65 HV, and then simply we do this. Well, we have for the recrystallized fraction 0 for the first for time 0, and then we have the fraction equal to 1 for 60 minutes time, and then for the remaining cases we just take the difference divided by the total drop. So if we go from 180 Vickers to 160, this is a 20 Vickers hardness drop, and then we divide 20 by 65, and we say that it's this 31% decrease is an increase of the transformed fraction of 31%, and we do this for all the remaining values to complete our table. So once we do this, we can plot the transformed fraction y as a function of time, and we can see that in fact it shows a sigmoidal behavior, which looks a lot like the idealized, which looks like the schematic version of the JMAK equation, which was shown previously. So we can try to obtain this JMAK equation in linear form, and then we can try to determine the constants by a linear regression analysis. In linear form, the JMAK equation is given here. We just rearrange the terms and take the logarithm of twice in the process, and then we can see this is a straight line of the form function of x equals ax plus b. If we note that fx is the logarithm of minus logarithm of 1 minus y, a is simply n, so the angular coefficient is n. The b is the logarithm of k, and the independent variable x is the natural logarithm of time. So with these relations, we can produce a new table which relates this function of x, which is obtained from the transformed fraction, with x, which is obtained from the transformation time. We get some null values here because we take logarithms of 0 and then it messes up. But we have these 3 valid data points with which we can work. So it's a good idea so this experiment is good because it's very simple and we can use it to other metals, for example copper or aluminum or steel, and we can follow this process by simply having the transformed fraction related to hardness, and we can and then we can maybe even work with more data points to get a more precise estimation of the of the JMAK equation coefficients. So after doing the linear regression, the points do in fact fall on a straight line, and we have the values for the constants n equal to 1.74 and k equal to e to the power of -5, 0.0067. So the JMAK equation for this case is given here. So it's a very quick example just to show how this transformation data can be used to represent a more practical situation. And here we have some more examples of recrystallization data for magnesium alloy. So we can see what actual data looks like. So when we take hardness measurements, there's a lot of variation, and the curves don't really look like a perfect sigmoidal curve. But more or less, we can see here that we have a transformation which is slow to begin, which increases rapidly and then sort of stabilizes. So, and here we have more idealized or maybe data which were obtained with more precise measurements of the transformed fraction, which is taken from our textbook, so for copper. And we can see that for each temperature, this is important, for each temperature we have a different transformation kinetics. Now, just to wrap up, so these kinetics which were obtained for the JMAK equation, and which we showed to be valid for recrystallization processes, can be used to explain general diffusive transformations, including the transformation of austenite to perlite. So if we take the isothermal transformation diagram, or the TTT diagram, the time temperature transformation diagram for a eutectoid steel, for example, we can see that along a given temperature, the transformation takes place by this JMAK equation kinetics. What is happening here is that, for example, at point C, we have only austenite grains. Gradually, as we move along this line, perlite colonies start developing at the austenite grain boundaries until we have a completely perlitic structure. So this is it for this lecture. For our next classes, we are going to look into more details at the interpretation of these TTD diagrams for analyzing possible formations of microstructures in steels, and we will look also at some other transformation diagrams which can also be used. Thank you very much, and see you on Monday.